Okay, so I think we should start right now, and I'm going to present my screen. Is it visible by everyone? I hope so. Is it visible?
Yes, ma'am.
Yes, ma'am, it is visible.
Okay, okay. So, as the last class, we were talking about compound nucleus and direct nucleus, like direct nuclear reaction and compound nuclear reaction. So I will do more on that compound nuclear reaction, as I already told you before in the last class, that compound nucleus has a very large things, and we should know something more about the compound nucleus. And I did not start even what is basically compound nucleus and what is the details of compound nucleus in the last class. So that's why I will talk to more today about these things. And obviously there should not be again any question and answer session, and I thought that in the previous lecture of today's I think assignment 6 week 6 was there by Archana ma'am. So I think you all have joined in that course, and there question and answer session was there. So I thought that I should tell something more about compound nucleus. So that's why I'm just going to tell right now what is basically compound nucleus and what is basically compound nuclear reaction is, and the more details of that, like Braid-Wigner formula, and then Ghoshal experiment and all these things. And it may be helpful for you in future as well as in right now also. So okay, so that means at first compound nucleus. Okay, like compound nuclear reaction, I think I have said something more about compound nuclear reaction in the previous class, that how it is forming and how the compound nucleus is forming in so these things, like, and what is the procedure behind the compound nuclear reaction, I have already told you. But still, as you people can miss, then I am telling again that for that the main property for compound nuclear reaction is that it should be okay. Someone is there. So the main property for that compound nuclear reaction is that it should be okay, just a minute, sorry. For the compound nuclear reaction, the energy of that projectile, I think I have read these things in the previous class, but still I am writing here these things again, that for that compound nuclear reaction the C star will be there, and then capital Y plus small y will be there. So here, as I already told you, small x is the projectile. Is there anyone who is asking something? Aviram, do you want to ask something?
No, ma'am.
Okay, okay, okay. So just to mute yourself, otherwise I thought that there is some question. Okay, thank you. Yeah. So,
No, I am unmute.
yeah, okay, fine. So here, as I already told you, that this is the projectile, and capital X is the target nucleus, and here small y is the outgoing particle, and capital Y is the residual nucleus. Okay, residual nucleus. So these things are there, it is already discussed in the previous class. So here in that compound nuclear reaction, what is basically doing, like I'm drawing a capital X here. Okay, So this is the capital X. Capital X, like target nucleus is there, and we are going to project this small x into that capital X. As the small x energy is very low, so that means what it will be like, small x can totally absorb by that capital X. So capital X means like, let's say inside that capital X there are so many nucleons is there, and obviously if I think that it follow the cell model structure in the nuclear reaction, so that capital X has so many nucleons which has again so many energy levels. So what it will happen that small x will be captured by the capital X, totally absorbed, it will be totally absorbed by that, and then what will be happen that all the nucleons inside the capital X, that means all the nucleons inside the target nucleus will be disturbed, because obviously one small x is coming from the outside, which has obviously non-zero kinetic energy, and also it will give energy to all the nucleons inside that capital X, and it will like as a whole the capital X will be unstable, and unstable means like all the nucleons will be collided each and every one, and obviously there will be some excitation level, and from ground state to excited state all the particles will go on, and all these things will happen there. And also but there will be one stage where capital X and small x will be in a compound condition, like capital X and small x. So this type of things will made a C star. Obviously this C is called a compound nucleus. But why I am telling a C star here, because a compound nucleus will be always in the excited state. Why it is in excited state? Because as you already know that when a target nucleus is there and a projectile is coming into that, then there will be an unstable state, and unstable state means there will be some collisions and some new ground state to excited state configuration, and all these things will be there. So that means as a whole it will be an unstable state, and unstable state means whatever it will be made in there, it will be, just a minute. Oh. Whatever it will be there, it will be in an unstable state, that means it will be in excited level state. So that's why for all the cases, just a minute. This. So for all the cases, compound nucleus will be always in excited state. That's why we are writing C star here. Now what will happen that C star will give a very large amount of collision, as well as the for each and every collision there will be some energy released, and all the things will be very unstable. But after some time, what it will be, it will decay into two particles, like let's say capital Y and capital small y. So whatever I have written here, that C star will go to capital Y plus small y. So these type of things will be there in the compound nuclear reaction. So right now what I am going to tell you that as I already told in the previous class, that it is indeed a independence hypothesis followed by that compound nuclear reaction. So So what is basically independence hypothesis? The independence hypothesis is like that. We are here that capital X plus small x going to C star, which will also decay to capital Y and small y. So the independence hypothesis says that the decay of that C star to capital Y and small y is totally independent of how it has formed from capital X and small x. So after formation of that C star, it will totally forget that in which process it has formed. Like it does not remember that in which state it was there, capital X and small x. It totally forget about these things, and it will decay to capital Y and small y, which is totally independent of the formation of C star, how it is formed. So this is known as the independence hypothesis. So I will prove that independent hypothesis, that it is indeed independent hypothesis is indeed experimental verified things. So and it was experimentally verified by Ghoshal, so S.N. Ghoshal, so that's why it is known as Ghoshal experiment. But before going to the Ghoshal experiment, I will tell about something. Let's say Brede-Wigner formula. So what is basically Brede-Wigner formula is? Like if you people have any question, you can just ask me, as I already told you so many times before that classes also. So now I am right now Brede-Wigner formula. So what is basically Brede-Wigner formula? Brede-Wigner formula is okay. Brede-Wigner formula is nothing but the calculation of the cross section of the nuclear compound nucleus. Okay, compound nuclear reaction. So in that compound nuclear reaction, we have to calculate the cross section of that process. So this is basically how I can calculate the cross section of that nuclear reaction. It can be told by that Brede-Wigner formula, and there is a formula for that cross section, and after knowing that cross section, we can tell that okay, we can have the information about that compound nuclear reaction. In that Brede-Wigner formula, like I can tell you why it is. Yes. See, in any compound nuclear reaction, there is two steps. First step is what? First step is the formation of compound nucleus. Formation of C star. C star is the compound nucleus, so that means formation of C star. And the second process is that decay of C star. Right? Like at first capital X and small x will combine to form the C star. This is the formation of C star process, and after that decay of the C star will be there. That means C star will be go to capital Y and small y. These two steps will be there in any compound nuclear reaction. So if I just calculate the cross section of the whole process, let's say cross section of sigma xy. Why I am writing like that? Sigma xy. You can just remember this notation. X, y. I think you have all know that what this reaction notation means. This notation means that the target nucleus is capital X and projectile is small x, and the residual nucleus is capital Y, and where is the outgoing particle is small y. So this type of reaction is there, but I am going to write now the cross section for the whole compound nuclear process. So for the cross for having the expression for compound nucleus, what we should write? Here the two steps are there. In that two step, as I already told you, that independence hypothesis tell us that 1 and 2, these two steps are totally independent to each other. So that means if I write sigma of xy, that means whole cross section, we can divide this in a two part. One part is the cross section for the formation of C star, and the other part is the cross section for decay of C star. So these two processes will be there, and we are going to just multiply these two processes because they are totally independent of each other. So as a whole, sigma x y is sigma x into, let's say, eta y. Eta y is nothing but the cross section for the formation of cross section for the decaying of C star, and sigma x is what? Sigma x is the cross section for formation of C star. So these two things are there. So we are going to calculate right now what will be the value of sigma x y, which obviously mentioned by Brede-Wigner formula. Okay. So just go through that formula here. So what is basically sigma xy? So sigma xy is nothing but sigma x into eta y. So at first I will calculate what is sigma x, and then I will calculate what is eta y. Basically, if I want to say that eta y is nothing but gamma y divided by gamma, where now gamma is what that I will tell right now. So let's say sigma. Okay, so at first I am going to say about sigma x. Okay, so what will be the value of sigma x in that compound nuclear reaction process? So for calculation of sigma x here, I should draw one diagram so that it will be clear to all of you. I'm not that much good in drawing all these things, but still I'm trying. Let's say it should not be in that thing, it will be in straight line. Okay, no, I should write it very clearly. Just a minute. So this line is okay. Inside that there is all the states, fully filled states. These are the all fully filled states. Basically here when explaining compound nuclear reaction, we are talking about cell model structure for the nucleons, okay, inside the nucleus. And this one will be one line, and let's say this one will be another line. So what is these lines? This is basically the ground state of C, and this is the excited state of C, and this is X. I will tell what is this is. Okay, so this type of things after writing there I can explain. Let's say EC. Okay, EC will be that much, and A6 is that much, and EX is that much. Okay, so what is these things? Okay, so this is basically whatever I have drawing here in that diagram. What we are seeing that in that diagram a cell model is there. In that cell model, like these two, this one and this one, these are the two potential well. Okay, in that inside that potential well we are going to see what will happen when a compound nucleus will form for a nuclear reaction. So this is the ground state, this is the ground state for that C. Like C means that the compound nucleus which is formed by the small x and the capital X combination. So here the energy of that EC, like EC means energy of the compound nucleus, it should be EX plus SX. So what is EX and what is SX here? EX is the energy of EX. I have written here that one, this one is the EX. EX is what? This is the excited state of C, and X is there, X level is there. X level is there means the energy of the X which is coming from the outside. The projectile X has the energy of this energy level. So this energy level and the excited state of C has the difference, and this difference is known as EX. So and what is SX is the separation energy of the X from the ground state of C. So EC obviously will be EX plus SX. So this like EX means the energy which is absorbed by the capital X from the small x. So this is the EX, this is the EX, And what is Sx? Sx is the separation energy of the projectile from the ground state of C. So obviously the whole energy of the C will be Ex plus Sx. Okay, fine. So this is for the initial particle, like capital X plus X will be C star, that type of things. EC will be Ex plus Sx. But if I write here after the decay, like after decaying C star, what will be the energy levels, then it will be like very similar, that this and here will be the excited state, and let's say this is the small y energy level. So what will be now, right now the Ey will be this one and Sy will be this one, and then as a whole that it is Ec will be this one. So that means as a whole in the expression, what should I write? Ec equals to Ey plus Sy, just very similar to the previous one, that Ex plus Sx. So here also before the formation of C star, like up to the formation of C star, what will be the energy of the C? The energy of the C will be Ex plus Sx, and the very similarly when it will decay, the energy of the Ec will be Ey plus Sy, like the energy absorbed by the capital Y due to the small y, as well as the separation energy of Y from the ground state of C. So this expression will be there, right? Now what will be happen? Now we are going to calculate, we are going to focus on this state, this state, let's say it is a psi t. Like I think you all know about the quantum mechanics little bit, so I will tell these things, that it is a wave function configuration, and we will write the Fourier transformation and inverse Fourier transformation of all these things. But before that, I am telling that psi t is the wave function for the for that excited state of that C. That means for the C star, the wave function for C star, the wave function is psi t. Fine. So what should I can write here about psi t? So psi t is nothing but as a like it can be separated in two form, like one will be in time space and one will be in space. One will be in space and one will be in time. So the space part will be psi 0, and e to the power, the time part, e to the power minus I e 0 t by h bar into e to the power minus I gamma, no, it should not be I, okay. So e to the power minus gamma t by 2h bar. But why e to the power minus gamma t by 2h bar is coming here? Because in that compound nuclear reaction, what will happen, that after some time C star will decay into capital Y and small y. So it is not basically, whatever I am talking about, this state is not basically a stable state, it's a decaying state. So if decaying state is there, so that means obviously the decay width will be there for that energy level. So gamma is the decay, like width of the energy level, okay. So that's why we are writing here e to the power minus gamma t by 2h bar, because gamma by 2 is the half width of that energy level, and it will be in a decaying mode, because we are going to say that after some time C star will decay to capital Y and small y. So that's why the expression is like that, psi 0 e to the power minus e0 t by h bar and e to the power minus gamma t by 2h bar. I think all of you understand these things. So we can write psi t as a space part as well as the time part, as well as there is a extra term which is due to the decaying of the state, like it is basically a damped harmonic motion, you can say like that. So psi t we can write like equation number 1. Fine. Now what should I write? And also again whatever we have drawing here, that excited state of C, that means C star. So sorry, I have mentioned these things here, this one, I am focusing this one. Okay, so this state I am writing here. So this is the excited state of C, that means C star. So C star has obviously it is not basically a stationary state, as I already told you that it is a decaying state. Okay, but this decaying state can also form with the superposition of all so many stationary states. So it is obviously the one of the properties of nuclear quantum mechanics. So that means we can write psi t as, let's say, a integration of a e to the power minus I e t by h bar dE. Okay. So I can write like that. This is the superposition principle. Okay, so here energy will go from minus infinity to plus infinity, because we can have the so many energy levels in between that energy e to e plus dE. So this is the expression for psi t for a stationary state, superposition of the stationary states. So this will be the psi t. Now from that psi t we can calculate what will be the value of ae, right? How can I find that? Like ae will be obviously, like if I just Fourier transform, like e to the power minus I e t by h bar into dE is there. So if I just Fourier transform the whole things, then what it will be? It will be like 1 by 2 pi integration minus infinity to infinity, then psi t prime, like let's say it is a different state, e to the power minus I e t prime by h bar and t prime. Okay, so these things will be there. So what is psi t prime? As I already told you that psi t prime has the expression like that one, psi 0 e to the power minus e0 t prime by h bar e to the power minus gamma t prime by 2h bar. Just putting all the things here in our calculation, we can have the value of ae is like, I'm not doing all the calculations here. It is just like e to the power minus infinity to infinity, then psi 0 e to the power minus e prime t by h bar e to the power minus sorry, not I will be there, gamma t prime by 2h bar, then e to the power minus I e t prime by h bar, then dt prime. So this type of things will be there. So this is the calculation for ae. Okay, okay, just a minute. So this is the calculation for ae. Now if I just calculate these things, it is a simple integration, that if I just collect all the things like e to the power minus I e prime plus a gamma by 2 into t prime and all the things, if I just calculate if I just collect in one position, and then dt prime integration is there. And obviously if it is dt prime integration, then the integration should be from 0 to infinity. It should not be from minus infinity to infinity, because as we already know that time can't go as a minus infinity, as a negative value. So that's why it should be in the limit of 0 to infinity, and the integration will be on dt prime. So if I just calculate all the integrations value here and all the things, then it will come like, I'm just writing the expression here. Okay, it will be, yeah, this one. It will be psi 0 by 2 pi e to the power I e so this is the e prime er, like what is it is there, this one we have just mentioned that it is the EC. Let's say, like, sorry, not this one is the EC. Why EC? Like the energy of the compound nucleus. So if I write EC here, then after all the calculations, what it will be? E minus EC, then plus I gamma by 2 T prime by H bar. I am just copying these things because you can just calculate these things by your hand. It's a very simple integration, divided by E minus EC plus I gamma by 2 by H bar, and the limit will be from 0 to infinity. So this type of things will be there for AE calculation. And if I just put the value of T prime as 0 to infinity, then it will have some value. So after putting all the value, all the things here, the calculation will be like that. AE AE will be psi 0 IH bar divided by 2 pi E minus EC plus I gamma by 2. This is the calculation, this is the expression for AE. Like after calculating all the things, it's a very simple calculation. If you just go through any let's say any nuclear and particle physics book, you can find the expression. So this is the AE. Now what will be the value of sigma x here? Our main aim was that sigma x obviously will be proportional to mod of AE square. Okay, so that means if I just square this one, then it will be proportional to mod of AE square. So sigma x will be like it is a proportional to, so that means some proportionality constant will be there, but I am writing here only the proportional things. That what will be there? Psi 0 square divided by 4 pi square, then 1 by E minus EC plus I gamma by 2 whole square, and there will be one H bar square, right? Because it's a mod square, so that means I will not be here. So this is the expression for sigma x. But if I just remove that proportionality symbol, then obviously one proportionality constant will be there, proportional constant. So that means if I just write here that constant as p, then we can write the value of sigma x as well, like that. Like sigma x will be p divided by E minus EC plus I gamma by 2 whole square, something like that, because all the things will be as a constant, like sigma 0 is constant, 4 pi constant, H bar is constant. So as a whole, p will be as a constant thing, and it will give us a result that sigma x will be, let's say, p divided by E minus EC plus I gamma by 2 whole square. So this is the expression for sigma x. So now what we will do, like we don't know about p, like this is the proportionality constant, that is fine, but what is the value of p? We have to calculate this one also, like what is the value of that constant, and how should I know that what will be the value of p? So for that case, like we will do one thing, like we will just go behind somewhere, and after that we will go forward to find the value of p. So the determination of p, to determine the p, we will just write something here that in any experiment, like in any nuclear reaction, compound nuclear reaction or any nuclear reaction, what will be the probability? Like probability means like one enclosure is there, let's say the enclosure volume is omega. Okay, so this is the enclosure volume. So in that enclosure volume, what is there? This is the enclosure volume. The enclosure volume is omega, and the number of possible states in that incident channel, like for that compound nuclear case, the incident channel is this one. for compound nuclear case, the incident channel is capital X plus small x, which will give C star. Okay, so the incident channel is capital X plus small x channel. So in that channel, what will be the number of possible states we have to calculate first, and after that with that we have to just multiply the probability of being a reaction in that state. So as a whole, what will be that? As a whole, it will be the cross section, like it will be the total probability for having the nuclear reaction in that particular state, in that particular volume omega. Okay, so, for doing that omega, the number of possible states in that nuclear reaction process, what will be the value? The value will be like sigma x Vx divided by omega. What is Vx? Vx is the velocity of the projectile, and sigma is the cross section for that reaction, and omega is the enclosure volume. Okay, so sigma is Vx by omega. It is basically what? It is the probability of finding in the volume in omega. It is basically the probability in the finding the particle in that possible energy state. So sigma x Vx by omega. Now it should be multiplied by dn. Dn is what? Dn is the number of possible states in that particular enclosure volume, which is omega. So if I calculate this calculation, then what will be that? Let's say at first, what is dn? Dn is basically nothing but, like, it will come from the statistics, Boltzmann statistics. So the calculation is 4 pi p square omega d into px divided by 2 pi h bar and then whole cube. So this is the value of dn, right? So if I just calculate that expression, that sigma x Vx by h, sigma x Vx divided by omega into dn, that will be the probability of formation of compound nucleus in that given channel, that capital X plus small x, this channel, and the probability of formation of the compound nucleus is this one, sigma x Vx by omega into dn. Okay, so this is the expression. So if I calculate this, there will be a large expression, and after calculating all the things, that there will be also a integration, like total probability. If I calculate the total probability, then the integration will be with the dn. Okay, so in that dn, the de is there, so that means energy integration will be there, and energy integration means minus infinity to plus infinity will be there, and all the calculation is there. So after doing all the calculations, this expression will, like, it will be expression which gives a total probability of formation of compound nucleus in the capital X plus small x channel. Okay, so this obviously is equal to what? This equal to that capital P divided by h bar square gamma lambda bar square, where what is lambda bar? Lambda bar is that one, lambda bar is that one. It is given here, that lambda by 2 pi. Okay, and how can I found the lambda here? The lambda will be coming from that expression, that E equals to 2 pi by lambda. So from that calculation, the lambda will be there, and lambda bar will be there, lambda by 2 pi expression, and all the calculation will give us the expression like that. And what is this expression? This expression is the total probability of formation of compound nucleus in that given channel, in the incident channel. So it will be equal to what? It should be equal to, like, total probability, it should be equal to gamma x by gamma. What is gamma? Gamma is the width, like for gamma x is like the width of the energy level of x, and what is the capital gamma here? Capital gamma is the width of the C, like energy of that C, compound nucleus. So if I just calculate these two things, then we can have the capital P value. Then capital P value is nothing but that, if I just calculate all the things, then it will be, it is the gamma x by h bar. So it is the lambda bar square gamma and gamma x. So this type of things will be there. So now we can have the expression of sigma x. Then what is the sigma x? As I already told you that p is there, so we have found that p value here. Then lambda square gamma x divided by e minus ec whole square plus gamma square by 4. This is the value of the sigma x, and this is basically the Brad-Wigner formula. And in that Brad-Wigner formula, we are not talking anywhere about the spin of the particles, like spin of the capital X, spin of the small x, spin of c, spin of y, spin of capital Y. We are not talking about all these things. So we are just talking about the spinless particles here. But if the spin will be there for any particle, like obviously in that expression capital X plus small y, small x will be c star. So if there is any spin, let's say for a capital X or for small x, then what will be the expression for sigma x? Then obviously the spin, like if I write the spin of x as ix and it is for ix, then what will be the value of sigma here? Sigma x. Okay, so sigma x will be like what is the value here? Pi. Okay, pi lambda bar square, then gamma x divided by e minus ec whole square plus gamma square by 4. Now what it will be, like one term will be added. The term is e2ic plus 1 divided by 2ix plus 1 into 2I capital X plus 1. This is the multiplicity value, multiplicity. So IC is nothing but IX plus IX. Okay, so if I just have any particle which has spin, let's say capital Ix, and the projectile which has the spin capital I small x, then when it will form as a compound nucleus, the spin of the compound nucleus will be Ic, which is I capital X plus I small x, and the cross section for whole the process will be like Ic plus 1 divided by Ix plus 1 into Ix plus 1 into pi lambda bar square gamma x divided by e minus cc whole square plus gamma square by 4. That type of expression will be there for the compound nucleus cross section, only for the formation of the C star. I am talking right now about the formation of C star because sigma x is there. And now I will go to the sigma eta y. Eta y is what? The decay of the C star. As I already told you before that there is two step, formation of the two step. I think I have mentioned here somewhere. Formation of the compound nucleus is in two step. Yeah, this one is the formation of C star, like formation of the C star as well as the decay of C star. So formation of the C star is giving us the sigma x, and the decay of C star will give us eta y, the cross section. So right now we will talk about what is eta y, and then we can find this formula sigma xy. Okay, so just multiplying these two. So so that means sigma xy will be sigma x into eta y, and eta y, sigma x is there, as I already told you. Sigma x value is already I have mentioned. So eta y means what? Eta y is nothing but gamma y by gamma, like how many probability of being a particle in the decay of capital Y plus small y with respect to the total decay rate. So that means gamma y divided by capital gamma. So this is the expression for sigma xy, and this is basically the Brad-Wigner formula. And in that Brad-Wigner formula I can write something here, just a minute. In the Brad-Wigner formula, basically what is there in that sigma xy expression, we can see that something like in numerator there is something, and in the denominator one term is there, this type of things, sorry, E minus EC whole square plus gamma square divided by 4. So this type of expression is there. Then if any condition is there that E equals to EC, then what will happen? It will happen as a resonance condition. So in that resonance condition, what will be there? The sigma will be very large. That means in the resonance condition, the cross section for that compound nuclear reaction will be very large, and it can be diagrammatically expressed like that. See, this is the, let's say, all the field energy states and all the things is there. Now as I already told you that these things I have mentioned here, that this is the excited energy levels of the compound nucleus C. Okay, so let's say capital X is there, which is the energy of the capital X. If it matches with the any one of the excited level of C, then there will be a resonance. Okay, in that resonance, what will be the graph of energy? The graph of the energy will be like that, this. So you can see that here the energy at E equals to EC. At that condition, the probability of getting the compound nuclear reaction will be very large. That means this is the resonant condition for compound nuclear reaction. So this is basically known as a resonant condition, and obviously it can come from the Breit-Wigner formula as a special case, like if capital E is equal to capital EC. So this type of things are there. Okay, so like I think I have talked a little more, so if there is any question or if there is any doubt, you can just ask me. Like till now I have just mentioned about the Breit-Wigner formula, how we can calculate the cross section of any compound nuclear reaction, which is nothing but the multiplication of two terms. One is the formation of C-star cross section, and the second is the decay of the C-star cross section. As these processes are independent to each other, that's why we are multiplying these two both. And next I have talked about if we have the spin of capital X, small x, capital Y, small y, EC, like C star, then what will be the expression for the sigma xy. So I have talked up to that much, and I think if there is no question, I will go for Ghoshal experiment. Ghoshal experiment is nothing but the proof of independence hypothesis for compound nuclear reaction. Okay, so Ghoshal okay, I think I should go for Ghoshal experiment maybe. So this is the Ghoshal experiment. Okay, so in that Ghoshal experiment, what is the outcome of Ghoshal experiment? The outcome of Ghoshal experiment is like that compound nuclear reaction indeed follows a independence hypothesis. Okay, so what Ghoshal experiment basically is, like S.N. Ghoshal and his team, what he did that he just made one compound nucleus. I'm taking an example, like whatever he have taken, I'm just taking the same example obviously. So nickel 28 plus helium 4. Helium is obviously that alpha particle I'm talking about. Okay, so it will come as Zn star 6430. See, Zn star is there, so that means it will be in a excited state, and it is basically a compound nucleus. Okay, and he has done this type of reaction, and another reaction he has done, which is this one, 29 plus H11 is proton, Zn star 6430. So this reaction he has done. So that means these two nuclear reactions he has just experimentally observed that what it will be and what will be the nature of Zn star for the two cases. Okay, and in next stage what he has done that. So these two expressions is the formation of Zn star, that means formation of compound nucleus. Now we have to decay, like Zn star will obviously decay to another particle. Now what he has done that Zn star can decay into so many types, so many particles. Like I can tell you, Zn star in their calculation, in their experiment, what they have got, this one, Zn63 plus neutron, or Zn62 plus 2 neutron, or copper 62 plus 1 neutron 1 proton. There are three types of things which they have just found after the decay of Zn star as a compound nucleus. So these type of things were there in the Ghoshal experiment. Now I will tell little bit more about these two reaction at first, and after that I will tell about these things. Now what is there? Like, see, the independence hypothesis, if it is true, then obviously it will say that the decay of Zn star, that means the decay of Zn star into, let's say, Zn plus n, it will totally independent of the nature of its formation. Like, nature of its formation means, as we already seen here, that the formation of Zn star was done by two ways. Like, it may be from Ni plus He, or it may be from Cu plus H. So they were just trying to show that the formation of Zn plus n, like this one, will not depend on these two processes. This is the main motivation for their work. So, and obviously it has successfully experimentally verified that independence hypothesis indeed present in compound nuclear reaction. Now how it will be proved? Like, I'm a little bit doing the calculation here, it's not that much calculation. So what it will be like, okay, I'm just writing here again, alpha Zn star, and then copper plus H11 Zn star. Okay, then the energy level I'm drawing here. The energy levels are like that, and this one. So this is Zn and this is Zn star. And what is this one? This one is, let's say, copper plus helium, and this is nickel plus alpha. So this energy and this energy, and basically this energy, this two energy is basically 7 MeV what they have measured. Okay, so the two energy levels difference is 7 MeV. So when we are going to produce Zn star through Ni plus alpha, then it is taking 3 to maybe 33 MeV, I'm not exactly sure, like that type of things will be there. And for this expression, like for copper plus proton, it will give Zn star. For this type of expression, the energy needed for making that a compound nucleus will be what? Will be, no, I think I have taken a reverse thing, like it will be 33 to 33, and this will be 3 to 33 plus 7, like 10 to 40. MeV, something like that. It's a range of energies. So that means basically the energy difference is 7 MeV, and we have to give 7 MeV energy more to have the second process, first process, and for the second process we need 7 MeV energy less. So this type of calculation is there, and they have just made these experiments very well, so that it will happen, it will form Zn star. Now what they have written like that: EC, as I already know, that E alpha plus S alpha. For this first one, I am talking about E alpha plus S alpha. Why? For the first one, the projectile is alpha, so that's why. And for the second one, what is that? EC equal to EP plus SP. P is the proton. Okay. So these things are there. Now EC is same. So that means E alpha plus S alpha equals to EP plus SP. Now from here we can write the expression of E alpha as EP plus SP minus S alpha. Now as I already seen in that diagram, that EP plus 7 MeV. Why 7 MeV? Because SP minus S alpha is nothing but this one. SP means this one, and S alpha means this one. So that means that the difference is 7 MeV. So we have written like that: E alpha equals to EP plus 7 MeV. Then what will be that? E alpha minus EP will be obviously 7 MeV. That's why we need 7 MeV extra for proton to have, 7 MeV extra for alpha particle as a projectile to have the reaction that is comparable to the reaction with proton as a projectile. Fine. Now, so this type of things is there. Now what they have done? Now they have done that Zn star can decay into various things like Zn63 plus 1n, Zn62 plus 2n, or copper 62 plus 1n plus 1p. Fine. So this type of expressions may be there. So they are like these 3 decay can be possible from both the above reactions 1 and 2, because from the 1 and 2 we can have this type of expressions. And the result, what they have got in their result, that shows, like I am just showing the result, and after that I will explain the result a little bit more. The result is like I am writing explicitly this alpha Pn. What is Pn? I will tell you. Pn sigma P to n sigma P Pn. Okay. So what is these things? Alpha n means alpha will be the x1 and n will be the y1. N will be the y1 means this expression, this reaction. So this reaction corresponds to the cross section like sigma alpha n, and sigma alpha 2n means that this expression. And what is sigma alpha Pn? Alpha Pn means alpha was the cross section projectile, and Pn like P and N. So this type of, if this type of expression will be there from the first expression means this one, then we can have sigma alpha Pn. The cross section for that expression will be sigma alpha Pn. And if I have taken the ratios of these 3, then it is exactly equal to the ratio which has given from which we have taken from that P, like second reaction. In that second reaction the projectile is P, so that means Pn, P2n, Ppn. So these 3 ratio will be exactly same as the previous one. This is basically the independence hypothesis. but how can I say that it is the independence hypothesis? So for saying that, I am taking a little bit calculation, that here these things is there, right? So if let's say at first these things is there for the first one, for the first reaction, like for the first reaction I am talking like capital X small x 6 star, then what will be the sigma xy? The sigma xy will be sigma x into eta y, right? And obviously sigma x will be like sigma x, yeah, that is fine. Okay, now I am going to write another thing, that in that second expression, what is there? X prime is different, x prime is also different, but sister is same. So what should I write here? X prime y, why? Because let's say we are talking about this expression, this thing, like Zn plus 1n, it is coming from the both of the reactions, both of the first two reactions. So if that type of condition is there, then y is the same, y is that one neutron, okay? So y is same, but x is here alpha particle and x is here proton. So if I write if I write that expression, then what will be the expression for that? Sigma x prime and eta y, as y is same, so that means eta y will be there. So let's say it is the third expression and it is the fourth one. Now coming to the outgoing particle different, no, like, okay, so now 3 divided by 4, if I 3 divided by 4, then sigma x y is to sigma x prime y, then what will happen? That sigma x is to sigma x prime, because it's totally independent of eta y, right? As eta y is cancelled out for the both cases. Like if I just divide these two things, then obviously ratio will be there, and ratio sigma x is to sigma x prime will be there. Fine. Now the second condition, in the second condition what is there? Like okay, this is the thing, and let's say x plus x will go to sister, which will go y plus y. Now coming to the second condition, that x plus x star, which is going to y prime plus y star y prime. So what will be the cross section for that reaction? Sigma x prime y prime, which is sigma x prime into eta y prime, right? Now, so I am talking only about, I am explaining only one condition. Let's say that nickel plus alpha Zn star, it is going Zn 63 plus 1n. This is the condition, and another condition is what? Copper plus H Zn star Zn 63 plus 1n. So in that condition, what is there? The thing is sigma of alpha n is 2. No, like from that calculation what was there, the expression was sigma of p of n equals to sigma of alpha is to sigma of p. Fine. So which is, so okay, so that means if I just write here, and also sigma of alpha and sigma of p is nothing but it is exactly the equal to the another process. Like if I take the another process here 2n, then it will also give that type of things. Like if very similarly if I just write sigma alpha 2n is to sigma alpha p to n, then it will give sigma alpha is to sigma p. Then by comparing these two, we can have sigma alpha n is to sigma p n equals to sigma alpha to n sigma p to n. So I'm just taking only one condition. There is so many conditions like that, like Zn can decay in so many decay channel. So for each and every case, that type of expression will be there, which is basically nothing but the proof of that independence hypothesis. Like obviously the cross section and how the decay of the Zn star is not depending on how it forms, like when whether it is formed by the nickel plus alpha or it is formed by the copper plus proton. It is not going to remember how it formed, and it will totally independently decay into any of the decay channel of Zn star, which is known as the independence hypothesis for compound nuclear reaction. So I think this is up to today. I think there is no question today. If maybe it may be possible that all the things are understandable by you, or it may be possible that nothing is understandable by you. So what is that among those two? I don't know which one is there. Like okay. Okay. So is there any question, like whatever I have talked till now, that at first Brede-Wigner formula, then Ghosal's experiment. Ghosal's experiment is nothing but the proof of that partially. Why partially? Like if there is any question, you can just ask.
Yes, basically up to mathematical part it was okay, but it was a bit lengthy lecture, kind of doing continuously mathematics and all that without discussion.
Yeah,
So it was partially. That is why it was partially.
yeah. Yeah, actually, like to explain the physical things or physics behind that,
Yes,
we have to calculate the mathematics a little bit. Like if
yes,
the
yes, yes. That is
mathematics
of
is
course there, but that makes people hazy during the lectures.
yeah. I know, I understand that obviously there are so many mathematics that at first quantum mechanics there, then Fourier transformation, then all the things are there. But I think I was just mentioning, like I was just emphasizing the fact that Brede-Wigner formula is what basically, and at last the Ghoshal experiment is what. Like obviously mathematical portion is on one side and the physics is in another side, so we have to understand the physics behind that, and obviously for understanding that we need the mathematics.
It's
So
yeah, that's true.
yeah, so okay, like if
Anyways, it was good.
if you people are not understanding, then I'm very sorry. Need a quick
No, no, no. We understood. At least I understood.
yeah, just
But
a minute.
it was making hazy because we are at home and you are delivering from your institution. So
Yeah, obviously
basically, the
it will be
in-person
a face
contact
to
is
face,
missing. For
yeah.
mathematics, in-person contact is very important.
If it will be a face to face, then it will be very good. And
Yeah,
also
yeah.
like I'm not writing that much very fast, and it is not that much good in that writing pad. Like if it will be a board like thing, then it will be very okay, but what should I say? There is nothing to do. Okay, I think some question is there from Aviram. I can't see, just a minute. Need a quick summary. Okay, I thought I have talked a little bit more and it was very fast, I think. Sorry for that. Okay, I am taking a quick summary of that lecture. The summary is nothing but in that lecture we were just talking two things. First one is that Brede-Wigner formula. In that formula we were just calculating the cross section of any compound nuclear reaction, and in that second portion we were just calculating, we are just proofing one statement that nuclear compound nuclear reaction is a independence hypothesis, like it obeys a independence hypothesis. So we were just doing that two things in today's lecture, and obviously in that Brad-Wigner formula there were so much mathematics, and after that the conclusion is like that this Brad-Wigner formula is this one, sigma xy, which is some constant, let's say there is some constant part is there, and in the denominator E minus EC whole square divided by gamma square by 4, that type of things is there, where E and EC is the variable here, and if the resonance condition is there, that means E equals to EC, then we can have a very large value of sigma x, which is the condition for resonance for the compound nuclear reaction. And this is about the Brad-Wigner formula. And for that Ghoshal experiment, what we did, like we were just want to prove the independence hypothesis for the compound nuclear reaction. And what is independence hypothesis? That it says that the formation of the outgoing particle as well as the capital Y is not dependent on the incoming particles capital X and capital small x. Like C star can't remember that what was like how it formed. Just as an example, Zn star was formed through two processes, Ni plus alpha and copper plus H, like proton. So these two processes totally forgettable by Zn star, and whatever was the outgoing particle for Zn from Zn star, that Zn plus neutron, Zn plus 2 neutron, or copper plus proton plus neutron, whatever it was. So it is totally independent of these two processes how Zn star was formed. So these two things were there, like first one Brad-Wigner and the second one was the Ghoshal experiment. And like Ghoshal experiment is nothing but a proof of that independence hypothesis for compound nuclear reaction. I think it is the summary for the today's lecture. I don't know it is understandable by you or not. Like, yeah, this simple two things were there. It is not that much difficult, but I was just doing some mathematics so that it may be understandable easy, but I think it becomes a hazy for you people. So okay. So if there is no question, then I can ask you something, that is there anything to discuss about the theory portion in the next class, or should I go with the question answer session for the next lecture? Physical meaning of independent hypothesis. Okay, the physical meaning means like Zn star, like compound nucleus, the outgoing particle from the compound nucleus will not be dependent on the reactions from where Zn star is produced. This is the thing, this is the independent hypothesis. And the physical meaning means you can say that like Zn star goes Zn plus n, Zn plus 2n, whatever it is, it can't remember that how Zn star is formed. Like this is mainly the physical meaning, like outgoing particle can't understand how it has formed, that type of thing. And I think it is like physical meaning means, like physical meaning is this one, that compound nucleus can't remember what is how they are forming, how it has formed before, and this type of thing is there. So if you can say that it is the physical meaning, that obviously it is a physical, means independent hypothesis is basically what I have just told you, but physical is this one, like Zn star will form, but it will totally forget that how it was formed. And the decay process, there will be so much decay process, different decay process, but each and every decay process totally forget that how Zn star was formed. So that type of thing. Okay, and I was just asking one question, that is there anything which I have to tell again to you people as a theory basis thing, like whatever we have told before, that direct reaction, and today the compound nuclear reaction. So just like that, is there anything else you want to know from me, or should I go back to the question answer session? Like I'm not sure that if you people will be very much benefited for that from that lecture, then it will be good that we will continue with the theory part. But if it was no meaning, it has no meaning, then we can go for the question answer session.
No,
So
no, no, ma'am. It is meaning. It is a meaning for
yeah,
the
yeah, sorry.
theory part. Yeah.
Sorry, can you please tell again? I can't hear, sorry.
Oh, I think. Uh, Hello,
Yeah, yeah.
my voice is clear, ma'am.
S-
Actually, it is very useful. The theory part is very useful for me, especially.
Sorry, can anyone please tell what he is telling? Mohammed, can you please tell?
Yeah, and theory part is very good for Mr. Aviram.
Oh, sorry. Okay, yeah.
This
So
has benefited him.
yeah. So that's what I just want to know from you, that which portion I should tell, like theory part or question answer session. If question answer session is good for you, then obviously I should go for question answer session, or otherwise I will go for the theory part. So
No, I believe, madam, you must go for theory part because TA first is solving the questions,
yeah.
and there are some quark models, how to solve those, typically how to remember the things and how to go on with the things, especially for quark models,
Okay, I think
reactions for the
yeah.
quark
I
models.
think sir has already started that quark model, right?
Yeah, that has already gone, and
Yes, yes, ma'am.
What?
yes, I has already started that.
Okay, so that means you want to know something more about quark model, right?
Yeah, in detail. Yeah, in detail. Some so that we can cross-examine the things and so that we can cross-question because
That's why I was
that is
just
a
checking. I was just asking to you that which portion you need to know from me. Like, obviously,
yes,
I
quark
can't cover
models.
all the things. Okay, I can't cover all the nuclear and particle physics in only let's say once in a week lecture. But I can help you in details something more, like if like quark model is there, then I can talk about quark model a little bit to detail.
Yeah, that will be beneficial for us to discuss the quark model and how to solve and what are the main tenets of solving the reactions.
Okay, like which type of expression you should remember for solving the questions
Yeah.
and all these things, right?
Yes. Yes. Yes.
Yeah. Okay. Yeah. And just one question, like till now, how much quark model has already done taught by sir?
We have already completed the quark model,
Yeah.
and
Sorry.
we are studying the Rutherford scattering.
Rutherford scattering.
Yeah. We have reached to rather mood scattering, Rutherford scattering. We have completed that.
Okay. Okay, and I
Yeah.
think when I will go on the next class, then it will be so much classes already covered, because the next class will be next Sunday, so that means only 1 week will be there. So I think 1 week
Yes. Yes.
means 2 or 3 classes will also be there by sir.
Yes. 1 week will be there.
Yeah, so that means like 2 or 3 lectures will be there, and you can know more about quark model, right?
Yeah, basically, because we have to appear in the examinations
Yeah.
in October, so lots of things are clear. For example, Rutherford model, hadron proton model structure, that's okay. But quark model, because there are lots of things. There are leptons, there are mesons, muons, etc. Properties of those things, quark model, that will be beneficial. Rest it is mathematics, and that is okay. That is fine.
Yeah, like
There's no problem in that.
I think myself that if you just clear your basic things, then mathematics will be done
And that will be
automatically.
okay. That will be
Okay,
beneficial. Yeah.
so like if theory part will be understandable by you, then mathematics will be done automatically. So
Mathematics is automatically done because it is good for physical science.
yeah, obviously, and I think the previous class is going to take by Archana. So Archana is doing all the mathematics there, like mathematics as well as
Yeah,
the history part.
she's helping out in solving problems.
Yes, so
But obviously, that is obvious that she cannot discuss the things in detail.
yeah, that's the thing, that's why I'm just asking that if it will be beneficial for you, that I should talk with the I should go for the theory part, then it will be good for you people. So that's why I was
Yeah,
just talking.
that will help in grasping the things.
Okay, so in the next class, so we'll talk about park model. Okay.
Correct model. Yeah.
Hello, ma'am. Hello, ma'am. So my voice is clear now.
Yeah, now it's clear.
Uh, so, okay, ma'am. So the basic thing in Quark model is how to use group theory in the Quark model.
Okay.
How to summarize on the basis of group theory. Because for me, actually, I have done all lecture before the starting this course on the NPTEL web.
Hmm.
Actually, I have also I make a notes. I have notes also.
Hmm.
So I know the upcoming lecture what is the talking. So, but the group theory is the something is less in the lecture.
Okay.
Uh,
Do you know about
uh,
Lie algebra?
yes, yes, yes.
Okay.
Actually, I know all the. I have a mathematical part of
Okay, you need the
it's.
physical part. Yeah.
No, yes, yes, yes. So, how to use group theory in the quark model and other also elementary particle to memorize this and to understand. So, this is the very beneficial for I think for us.
Okay. Okay. Sure. Sure. We will discuss in the next class about that. Okay.
So yes, and also it is good to the some program session on the direct and compound nucleus. Uh,
Program session means? Oh, problem.
Sorry, problem session.
Okay, problem session. Okay. So
Yes.
let's do one thing. That next class we will talk about quark model, and then next to
Yes.
next class we will talk about direct and compound nucleus problem session. Okay.
Yes. Yes.
Yeah, like one class will be in quark model and another class will be in problem session for the direct and compound nucleus. Is it fine?
Yes. Yes.
Okay. Okay, so for today, bye bye.
Okay. Now I think yes. Yes. Okay. I think my voice is clear now.
Yeah, yeah, your
So I
voice is
am
clear.
I now I am able to express myself and what I need.
Yeah, actually, you were
Yes.
talking in the chat box, and it is coming so much late, so that's why I'm not that much comfortable with you. So if you will
Yes.
talk in the face to face, then it will be good. Okay.
Yes. Yes. Okay, man.
Bye bye.
Bye.